Okay, so we are continuing section 5.5, and we are looking at some more examples here in section 5.5. One of the examples is example 3. Okay, and remember when you multiply a vector by a matrix, you're doing a transformation on that vector. And in example 2, there was a matrix who had complex eigenvalues and complex eigenvectors. Okay, and that matrix was it's a different example than the one we did, but just suffice it to say that this matrix A here, where they have x1 equals a times x sub 0, okay, and there's the matrix A. So what like if you multiply the matrix A by if you multiply the vector 2, 0, okay, maybe I'll make it a little smaller. So look below at the picture there. So 2, 0 is a coordinate on the x-axis. That's x sub 0. If you multiply it by this matrix A, you get the coordinate 1 and 1.5. So x1 is 1 and x2 is 1.5. Okay, now what if you were to then multiply the 1.0 and 1.5 by that matrix A? You're going to get the coordinates negative 0.4 and 2.4, and that's x sub 2 in the picture. So the effect, and then you can keep going. You can but the effect of multiplying a coordinate or a vector by this matrix A that has complex eigenvalues, okay, complex eigenvectors, is it produces an orbit. It produces an orbit, an elliptical orbit, okay, and that's just a comment that they're pointing out. But what's happening is rotation, right? What's happening is a rotation. The action of this multiplying this matrix, and let me just move this down here. The act of multiplying points, okay, by this matrix that has a complex eigenvalue, okay, is, well, it has actually complex eigenvalues, right? But that's fine. We'll just stay with what they're saying. The point is, what's the matrix doing? It's causing a rotation. It's causing a rotation. It's taking points and it's rotating them counterclockwise according to that pattern there. And there is a reason for that. There is a reason for that. In terms of terminology here in the book, you can have real and imaginary parts of vectors. Okay, so, and they, like we saw in the previous example, that, well, we had two complex conjugate vectors. Okay, but like real and imaginary part of a vector, you know the real and imaginary part of a complex number. But in example 4, okay, in example 4 here, you have this complex eigenvector. Okay, I want to be careful. It's not a, I don't want to call it a complex eigenvector. It's just a vector with complex numbers in it. And you can break it up into a real vector plus I times another real vector. But the 302 is called the real part of the vector x, and the negative 115 is the imaginary portion of the vector. So this terminology is could be useful, particularly for conceptual problems. The conjugate, I don't know if you've maybe seen this, probably not, but the conjugate of the vector x, the complex conjugate, they denote that with an x with a bar over it. Okay, so it would be what you see there. Okay, so just a little bit of terminology for you. Okay. Now let's talk about this rotational action that's going on. Okay, let's talk about it. I want to go down here to this example 6. Whoops, went too far. There we go. Example 6. So they say that if you have a matrix C with those values, where A and B are real and not both 0, then the eigenvalues of C are A plus or minus BI. Okay, so let's see, let's go to the whiteboard for a moment to justify that. Okay, so you have this matrix C with these particular entries. First column is AB, second column is negative BA. And you want the eigenvalues. So the eigenvalues come from the determinant of C minus lambda I being equal to 0. Well, that would be oh, whoops, hold on, that's not quite right. Oh, hold on here. Wait. One moment. Okay, that's what you would have. And so you know how to do the determinant of a 2 by 2. Okay, and so if we continue here, let me go up here, you're going to get a squared minus 2a lambda plus lambda squared plus b squared equals 0. Okay, so lambda squared minus 2a lambda plus a squared plus b squared equals 0. Now, let me just make sure everything's good here. Okay, and so again, we're looking at example 6 here, and we're trying to find the eigenvalues of this example 6 from section 5.5. We're trying to find the eigenvalues for that matrix C. Okay, so quadratic formula, lambda will equal negative of negative 2a plus or minus the square root of b squared, which would be 4a squared, minus 4 times a squared plus b squared, all over 2 times 1. Because the b squared, that's negative 2a, quantity squared. That gets you 4a squared. And then minus 4ac. Well, I think I need a little more, I want a little more, hold on here, a little more justification. Hold on. Let me just be a little more clear here. Hold on. I got to go to 3-point font here. It's so hard. It's not hard to change the font, but it's just kind of a. All right. So let's see. This was negative 2a quantity squared. That's b squared minus 4 times a times c, and c is a squared plus b squared. Okay, and so lambda will equal 2a plus or minus the square root of 4. No, yeah, it'll be the square root of negative 4b squared all over 2. Because this here, this negative 2a squared is going to give you 4a squared. And then this part here is going to give you negative 4a squared minus 4b squared. And so the 4a squared here will cancel out with the negative 4a squared, leaving you with negative 4b squared. Now this is going to equal 2a plus or minus 2bi all over 2. And yes, that will just equal a plus or minus b times I. Exactly right. So what I'm trying to do here is justify the, hold on, let me just put that a little 2 over here, okay. Just trying to justify what they said in example 6. They said for this matrix C that the eigenvalues are lambda equals A plus or minus BI, okay. All right, now I don't know if you remember, but the modulus of a I want to say it the right way. The modulus of a complex number. I'll tell you. Let me go back to the example because it's in there. It's in there fine. Any questions before I go on here? All right.
I don't have any question.
Oh yes. Question or no? Sorry.
No, I said no.
Oh, great, Jake. Okay, very good. Okay, so back to the book here. So now we are comfortable that lambda equals a plus or minus bi. And in figure 2 on the left, they've drawn, like, remember to draw a complex number, you just write the a and the b as a point. And then you have this angle. That's called this angle. Hold on here. I think that's called, I should know that. Var theta, I believe. Let me see here. Phi is, hold on. Let me go to the whiteboard here. Okay, this is in the recording. Phi, this is normally phi. But this symbol here How many have heard of var theta? Let me just check it real quick here. Hold on. I want to make sure I'm right on this. No, it's not that. I'm going into Google and I'm looking at the symbols, the Greek symbols. Maybe it is, let's see. Var phi, right, okay. No, it's not var theta. So you were almost right. Was it Mikhail who said what he thought it was? Yeah, this is not phi, but it's called var phi. Var phi. Okay, and if we go back to the, all right, very good. If we go back to the book here. So this is something that was covered when I was, taking math. But in the figure on the left, if I can plot a complex number in the XY plane, well, where the horizontal axis is the real part of the complex number, we're looking at figure 2 now on the left, and the vertical axis is the imaginary part of the complex number. So A comma B is the coordinate, and then var phi is an angle. Okay, how many recall seeing that maybe in back when they were in school, like high school? It's pretty common when I took classes. All right, well, you have a modulus too. So the modulus is that R. The R is like a radius, and the modulus is of this complex number is the square root of a squared plus b squared. Now what they do is quite interesting, okay? They say, okay, how does this matrix C, okay, let me go ahead and erase a few things here. How does this matrix C act on coordinates or vectors? Well, you can write that matrix C as the scalar R times that matrix where the entries are A over R, negative B over R, and B over R and A over R. But then you can write that as the diagonal matrix with entries R times that matrix with the trig functions of phi. Now, for instance, you might be wondering, how's the cosine of phi equal to A over R? So let's focus here. Hold on. Let's focus right. Sorry. Let's focus right here. Cosine of phi, they're writing that as A over R. Well, if we look at the picture on the left, the cosine, remember, is adjacent side over hypotenuse. So relative to phi, the adjacent side is A, the hypotenuse is R. So cosine of phi is equal to A over R. If you were to look at the sine of phi, okay, the sine of phi here, okay, if you were to look at that, sine of phi is B over R, because the sine of phi, sine is opposite side over hypotenuse of that right triangle, right? So opposite sides B, R is the hypotenuse. So basically what happens is this matrix C can be thought of that has complex eigenvalues. So this we can generalize this to any um, 2x2 matrix with complex eigenvalues. The matrix C can be written as the product of two transformation matrices. The first transformation matrix is, well, no, hold on. I want to be careful here. Remember, we're going right to left. So just get some of this off. The first transformation matrix can be thought of as a rotation, okay, through an angle phi. It would be a counterclockwise rotation. And then what you're doing with that counterclockwise rotation is you are multiplying that after you take the coordinate and rotate it a certain angle counterclockwise, then you scale the coordinate by the by r. Okay, so it's the matrix with complex eigenvalues. It's a composition of two transformations. First being the rotation, and then the scaling. Okay, effectively, this is what's going on. And they have here in Figure 3, they mention here a rotation followed by a scaling. You see that? It's really quite beautiful. Really quite beautiful. Okay, so if we go back to that second example, if we go back a little bit here, to that second example, when you take the matrix A that has complex eigenvalues and multiply it by the vectors, not only are your new coordinates, what are your new coordinates? Well, it's taking the vector and rotating it counterclockwise, okay, but then you are scaling it. Okay, you're scaling it, and so that produces, and you do that for every point, that's going to produce an ellipse. That's going to produce an ellipse. You see? See how that works? Are there any questions on that? All right. Well, let us do a little bit more here. Let us do a little bit more. I'm going to example A. Okay, I'm going to example A. And I'm not worried about invariance right now, but they mention that this matrix, and they would have used MATLAB to get this, this matrix has eigenvalues 0.8 plus or minus 0.6i and 1.07. Okay, so it's a 3x3 matrix. It's going to have it has in this case three eigenvalues, three distinct eigenvalues. And let me ask you this. Here's what I want to ask. If you had a 3x3 matrix A, could you have eigenvalues like this? 2 plus 3i, -5, and 4. Could those be eigenvalues? Are those possible eigenvalues for a 3 by 3 matrix A? Could that happen? What do you think? So you have one complex eigenvalue and two real eigenvalues. Is that possible? Okay, Mikhail thinks yes, possibly, and I appreciate all responses. Well, here's the thing. Here's the thing. I'm going to assume everybody's thinking yes, okay? Unless you tell me no, I'm going to think everybody's thinking yes on this, or possibly, okay? So, Mikhail, you have company. All right? Well, you're right. The answer is going to be no. Now, why is that? Why is that? It was a good try. What about this? Could you have 2 minus 3i, a 2 plus 3i, 2 minus 3i, and 4? Could those be possible? Is that possible? What do you think I'm going to say? What do you think I'm going to say on this one? Okay, why? The answer is yes. Why? Why? What's the difference between the first scenario, which is not possible, and the second scenario? What's the key difference here? That's right. That's right, Mikhail, the conjugate. Complex eigenvalues always occur in conjugates. If you get a 2 plus 3i, you're going to get a 2 minus 3i. Remember in calculus or in pre-calculus when you solved polynomial equations and you would get complex roots? Didn't the complex roots always occur in pairs as conjugates? Well, and it did. For this one, Mikhail, since it's a 3 by 3 matrix, you couldn't have more than 3 eigenvalues. You couldn't have more than 3 distinct eigenvalues because the characteristic polynomial would be of third degree. For a 4 by 4, yes, you could have complex conjugate eigenvalues and then 2 real eigenvalues. Yes, you could. You could. Okay, so are there any questions on this? Okay, well, that is section 5.5, and I will stop the recording on this. We've covered 5.5, complex eigenvalues.